So, welcome back from lunch. We're here to listen to Justin. Please welcome him.
Well, welcome. I can't see most of you now because I'm blinded by the lights. There, screensaver kicked in. My name is Justin Lee. I work for DataDog currently, and normally I like to poll the crowd, but I can't see you. So obviously we're here to talk about bytecode, and it's an area of interest to more than just me apparently. How many of you have really worked with bytecode before? That's what I thought, like 3 or 4 hands that I see. Great. It'll be a lot of fun then. So my title is a joke, and I like to make bad jokes, and all my friends will tell you that I like to make bad jokes. And it was I was encouraged to explain this joke because it may not translate well from the US. But if you're familiar with how the internal combustion engine works, there's 4 cycles, and in step 3 here, that's when the spark plug fires. And if it doesn't fire at that point, you get problems, right? And if it doesn't do that, it's called missing. That's the technical version of it. But the joke version can best be explained, as most of them can, by Scooby-Doo. So the mystery van was having a problem. Fred's trying to explain it to the crew. You see that hole? That should be an engine. It's like your engine's missing. Anyways, it's a bad joke, but that's what it means. All right, so just some brief history. I've been doing Java since 1996, since virtually there was a Java. And for most of my career, I never looked at bytecode, because why, right? Do you ever look at the assembly code of the stuff that you compile? It's interesting from time to time, but honestly, most of the time, who cares? But I worked for Red Hat for a long time, and I was on the Quarkus team from early on, which does, if you've ever used Quarkus, it does a lot of bytecode generation at build time to optimize startup times and yada, yada, yada. And so that's when I really started playing with bytecode. In particular, I was responsible for making initially Kotlin work with Quarkus. If you've ever tried to use the 2 of them, early on it didn't work well, but I was a Kotlin guy and I wanted to use Quarkus and Kotlin, so I started that. And that's a whole other ball of wax. But now I'm at DataDog. We do tracing and monitoring and observability. And I work on a product to enable live debugging of your production system, which I'm happy to talk to you about, but this is not a DataDog sales pitch. But basically involves dynamic bytecode modifications at runtime of a running system. So there's some very cool stuff that we do there, but it's all like bytecode stuff. Now, the reason I tell you this is, even though I know a fair bit about bytecode, I'm not an expert. There'll be some questions, I'm sure, that I may not know the answers to. But there's a whole lot of terrain in there. And we're just talking the bytecode, not getting into the memory model or, all the other stuff that JVM does. But this is the list of all the bytecodes as of Java 24. There's 150, 60. I lost count. Is the mic going weird?
Your beard.
Oh, it's my beard. I wondered. I'll just trim it. So these are all the bytecodes. There are 5 different ways that the JVM invokes a method, depending on what you're doing. And we'll look at most of these. I realize there's one that we won't look at, but it's a kind of a special case. This one was famously added in Java 7, which enabled lambdas more or less in Java 8, which is really nice, and also dynamic languages, Python, Ruby, Groovy on the JVM. But just looking at the operations for an int, you have all these bad boys, and then you add the longs, and then the doubles, and the floats, and then it starts to get weird. Internally, the JVM represents most of the integral types as int. So even a Boolean is represented as an int internally, mostly. Shorts, bytes, they all get widened to an integer, or to a 32-bit type for memory layout and word alignment reasons and such. And then, anyways, that's all of them. So I'm not going to do it all in slides because slides are awkward. to look at. So what we're going to do is we're going to look at a variety of different source codes. We're going to look at like just common structures and see what the bytecode looks like. Some of it's really interesting, and then some of it is like, well, it's not as magical as I thought it might be. And we'll see some patterns emerging out of that. So with that, let's take a look. OK. Now, I'm going to be referring to this off and on if my IDE will respond. Come on. It's fine. All right. It doesn't want to render it. It's fine. We'll just do this. That's mostly for me to give me a little bit of a guide. You can read ahead if you want. All right. So a basic class. This is, it's a class, 2 fields, getters and setters, nothing really there. Now, there are 2 ways that we're going to look at the bytecode here. How many of you know of the tool JavaP? OK. And I'm imagining fewer of you have used it. But it's a nice way to take the bytecode and dump it out of the binary format into a reasonably readable text format. So we'll look at a little bit of that. But there's another way that's a little bit nicer, depending on what you're looking at. There's a tool called ASM, that has some utilities that will dump out bytecode. Depending on what you're looking at, in a more readable format. And we'll look at both, because sometimes it's better to look at one versus the other. But more importantly, for those of you who want to play along at home, and you want to look at bytecode, you go back to work, for example, and you're like, what does this look like? I don't want you. I use a plugin. I use this plugin at work all the time. It's very nice. It's called Analyze Bytecode. I know it's very creatively named. But it does this very cool thing. It'll compile your file, and you get this little view of it here in the corner. And there's all sorts of interesting metadata that we'll take a look at eventually. But the important thing is it gives you this view. OK? But before we get too far down that, let's just take a look at the JavaP version of it, which we can find over JavaP version. There it is. So this is what the JavaP output looks like. So what I've done here is I have a JBang script that I run from my Maven compile to go find all the class files in it, that ASM utility I was telling you about. No, I'm sorry. It does 2 things. It doesn't matter. But one of them is it invokes JavaP for every class file it finds and can dump it out. So for every source file we'll see in here, there'll be an ASM output and a JavaP output. It just happens as part of the build. So this is what the JavaP output looks like. And as you can see, here's the version number. If you were in the Nikolai's talk earlier this morning with the Java version, this is 65, which is Java 21. There's no minor version. You can see here's the class that all matches. There are certain flags that a class has. In this case, it's public, because this is a public class. It can be private, of course. The super flag, I actually don't really know what this means. It might differ if it was an interface. But every class, as you know in Java, implicitly extends object. So there's always a super somewhere. There's a couple of constants. There's this class, the super class. You see there's no interfaces. We saw 2 fields. There are 5 methods and 1 attribute. OK, so the constant pool, it's interesting. But it reduces the amount of data that you have to get recorded into the class file, and you can reference and reuse and whatnot. There's a bunch of stuff there, and we'll take a deeper look at it as we go along. And then you have your field declarations. We'll take a look at it in the other format, because it's a little bit nicer. Some methods, and we'll go down. Anyways, this is the JavaP output. We'll come back to this in another example, because it looks better for certain use cases. But what we're really interested in is this other format. I left my mouse back in Brooklyn, which is what I normally use, and the trackpad is driving me batty. There. OK, so here's our Java source code, and here is the ASM version of it. Now, you can see we have a field answer, and we have int equals 42, string quote equals, that's no moon for you Star Wars nerds. But you'll see here, it lists the type as an I. I, capital I, is the bytecode representation of an int. So I is int, long is L, F is float, D is W. No, I take that back. Correction. You'd think L is long as L, but can you guess what long really is in bytecode? It's the obvious J, right? Clearly, that's the obvious answer. I don't know why it's J, except if you look at here, you'll see string, and it's not java.lang.string, it's this L java slash. This is the internal name, the descriptor, if you will, of that type. And when you look at bytecode, you will see both forms in different places. I don't know why they decided to make the distinction between the two. There's a couple of the Oracle Java people here. Maybe I hope they know. I should hope. Anyways, this is the internal form, and that's what you'll see most of the time inside the bytecode. So that's just what it means. You can strip the L and the semicolon, replace the slashes, whatnot. OK, so I don't want to assume, but most Java developers, once you've been around, know if you don't declare a constructor, you get one for free, right? The default no-work constructor. So that's what we have here. But you'll notice it's called init. That is the name for the internal name for the constructor of a class. Just bracket init, and you can have multiple ones if you have multiple constructors. And if you have a static initializer, it'll be CL init. It's basically a class init as opposed to an instance init. And that's the constructor declaration, and you can see it takes no arguments, and it returns void. In Java, we're taught like constructors don't return a value. It's a constructor, right? But in the bytecode, every method returns a type. In this case, it's void. So we start here. We have a couple of labels. You see line number. This is how the debugger knows like where to go whenever it stops or when you get your stack traces. The line numbers are encoded into the class file format. And then you can see line number 4, L1. So this is labeled L1. Line 4 in the source code, which you can see here. Now, you might notice that that is outside the constructor. What happens when you do field initialization is all those initializations get prepended to whatever constructors you might define. And I believe, I'd have to verify this, but I believe it gets prepended to every constructor. So the initialization will always, it has to really, I guess. So that your fields are always initialized before the constructor runs, and then your constructor body can do whatever, overwrite values if you want to. But this line number is actually way up where the field declaration is, up on line 4, which is kind of interesting. You can set a breakpoint there. We'll get to some of these other bytecodes in a moment, but you can see your BI push. It's pushing an integer onto the stack, and we're calling put field. And again, we see here the class name and the field. And it looks, I just closed the Java P. It looks pretty different in the Java P version. Sometimes it's cleaner. The ASM version makes it a little bit more readable. In the Java P, you'll see it says put field number 7. And then you have to go look up in the constant pool, which is why I like this plugin so nice, because you can look at the constant pool and you go to 7, and you can see, oh, it's a field ref. But the class index is 8, the name and type index is 9, so you go to 8, there's the name index for the class type, and it goes to 10. You can follow it down. There's a lot of jumping back and forth around. I don't claim to be an expert in the project-laden ahead-of-time compilation stuff necessarily. I've read about it. But when they talk about like the constant pool resolution stuff, I think this is what they're talking about, because it's a whole lot of like back and forth lookups that have to be resolved at some point, and once it's resolved, you can kind of store that in a cache. Right, so without belaboring that particular detail. And again, you can see here's we do the string. This A load is a reference load, so it loads the reference, and 0 is this. So it loads the this reference. It loads the constant of that particular value, and it puts the field value. So that the two values on the stack, whenever it does that, is first the reference, and then the value of the field that it's trying to set. And then once put field operates, it'll pop those off the stack and use those to execute that particular bytecode. Since there's nothing else in the constructor, there's a return, so we're done. Okay? There's some local variable stuff, but it'll get a little bit clearer here. So, all right, back to the source code. So in a getter, the standard getter. It's about as simple as a function can be, and we'll build on it. But you can see here, it's public. This will list you the access flags. So 0, 1, in this case, means public. There is, if you use this plugin, there was a button, one of these two, you can pull up a dialog and enter in a constant value, and given the context, it'll say, oh, for a method, it means this, but for a class, it means that. So if you see a raw number, you can decode it and see what it means. Most of the time, you don't need to. But, so it's line number 8, which starts here. And we're going to load 0. Every instance method has as an implicit parameter the 0th parameter of this, which you never see in your source code, but you see it in the bytecode all the time. And so load 0 says to load the this reference and put it on the stack. And then we are going to get field, in this case, the answer. So it's going to use the reference that we just put on the stack to go get a particular field as defined by the constant pool bouncing back and forth. I like this particular output better because you don't have to keep jumping back and forth with the constant pool, because it gets really weird later on when we start talking about lambdas and invoke dynamic. So it loads it. Get field returns that value out of that particular field on that instance, because it could be any instance, really. Not this, but it just happens to be in this case. And then leaves it on the stack. And then return is the bytecode for return an int value out of this method, in keeping with the return value here. And OK, so the local variable table is interesting, and it will also get increasingly complicated as we go. Now, if you have loops and stuff, you have variables that are in and out of scope, right? The local variable table is how it tracks that, in part. In this case, we have a variable 0, which happens to be of this type. So what you see here is you see the name of the variable, this, the type of the variable. The best way that I read this, and I'm sure I'm missing some nuances, is these are the two labels between which this particular variable is in scope and visible. And if you try to reference it outside of those two variables, that's when you get unknown variable or field type or whatever the error is. And the 0 just gives it which slot in the table it is. And this will always be the 0th slot. I say always. There might be a weird special case, but I've never seen it. And then max stack and max locals is some internal housekeeping in terms of how big of a stack that the JVM needs to allocate for things to help verify the class path, the class execution. Those details also can get very exotic, and we'll look at some interesting bits. But that's the local variable table on just this one, as simple as it is. Now, setter takes a parameter, so we get a little bit more complicated. So we load 1, and now we're loading 0, then we're loading 1. Now, load, as you might expect, says load an integer. And the 1 comes from this local variable table, and you can see we have local variable answer, which is the same as our method parameter over here. So that's parameter local variable slot 1. It is of type I or int, and its bounds are label 0, label 2 in slot 1. Now you can see we have a max stack of 2 and max locals 2 because we have this and we have the parameter, which gives us 2 local variables technically. Right. So we load this, we load the parameter, we put field, and then we just return because we're returning void. And that's the basic structure of a method in the bytecode. And it will get more and more complicated, I swear. If we introduce a local variable internally, we can come here, let's save it, and it will rebuild. So now when we come down to set answer, we have the load 1, store 2, but you might be wondering, what's that doing? So what happens here is we're loading the first parameter, and we're storing it in the local variable slot 2, which correlates to this line. And if you look down at the local variable table, you see we have a new entry called temp of type I between L1 and L4 slot 2. Now you can see local variable, or max locals is now 3, because we have 3 variables. And where this gets really interesting is, let me shift things around, if it'll let me. if you want to see what happens when you put things into a different scope, okay, before this happens, you can see local variable says L1 and L4, which is essentially the beginning of the method and end of method. If you put it in a block, like a for loop or whatever, in this case it's just a raw block, we can come in, really missing my mouse today. Go. Come down here, I load 2, put field. So we moved it down, and now here we store I2, variable 2, or the variable slot 2. Here's L1, and the end of the block is essentially L2, L3, depending on how you want to look at it. But if you look down here, you can see temp now is visible between labels 2 and label 3. And that's the only place that temp is resolvable. And if you go outside this scope and try to do anything with that variable, that's when you get the ugly red squiggles and red lines and stuff, because it's outside of the scope. So that's how that works. Now, this is a pretty basic class. Nothing terribly exotic yet. But in the keynote yesterday, how many of you were in the keynote? That was one of the coolest opening keynotes. I'm a metal fan anyways. But I like examples that are relevant and have, I think it's easier to understand when you have some connection to the example you're seeing. So what I wanted to do is I wanted to say, what does that bytecode look like, right? Because that was some pretty interesting most interesting hello world I've ever seen. So I ran the bytecode, ran JavaP to see what the bytecode looked like, and that bytecode looked like that. Anyways, I've been giggling about that joke for a day now, and I know it's terrible. I'm not ashamed. Okay, so that's a basic field. Let's take a look at, if I can use my keyboards. Let's take a look at some flow control, right? There are a few different ways, a few different structures we use. We have for loops of various forms. We have whiles, we have ifs, and I am going crazy. Close. All right, so let's take a look at this one. Flow control. All right, it just did it for me. All right, so we're going to ignore the constructor because we've been there. Oh, I did want to say, because I didn't mention it earlier, when we invoke a method, this is one of the 5 ways that we invoke methods. This is invoke special, which is used only for constructors as far as I know. There might be a corner case I'm not aware of, but this is the special call that the JVM uses to invoke constructors as it goes up the chain, all the way up to object. That's invoke special. We'll see the others in a bit. Okay, so to see a for loop. So we have a basic nested loop, I from 0 to 100, j from 0 to 100. So let's just briefly, we'll take a look at the local variable table. You can see we have I, we can see j. Now you might be wondering why does that order look the way that it does, right? I asked people who know more than I do about this, why? Is there some meaning to this? And the answer was, the internal list that Java-C uses is weird, and you get some weird ordering stuff. And that was the best explanation I got. So the order doesn't mean anything. It's just how ASM reads the stuff, and it gives you what it knows. I thought it meant something, but it does not. So that one's for free. Anyways, so we have I and j, and you can see that they have certain bounds already for where the bodies of the loops are. Now, what that looks like is this. So iconst 0 is kind of special bytecode. Just load the constant value 0. We're going to store it in 1, which is I. Now, I don't want to dwell on this because this gets really complicated, but you'll see in various things, you'll see frame append, frame sane, frame chop, blah, blah, blah. Those are internal housekeeping bits for the JVM, and it helps validate that you don't reassign variables to types that don't match. There are cases in the bytecode where it will reuse local variable slots depending on where you are in the program. And it uses this frame to help detect those boundaries so that within that particular frame, the type, you don't assign an integer to a string or whatever, for example. It's mostly internal housekeeping. And it gets very weird very quickly, so I don't want to dwell on it. Okay, so anyways, so we're gonna load that variable. There's the bi push for the upper bounds. Now, this is where the for loop magic happens. You'll see if, and this is a compare. It's an integer compare greater than equal. Now, if you'll notice, what's weird about that is the actual operation is less than, right? That's what's in the source code. But the bytecode says greater than, and that felt weird, and I was very confused about it for a while. But from my understanding, what's happening here is because we're pushing things onto the stack. And so the stack order matters when you compare, because the operands matter, because it's not a symmetric operation. So because it's a stack, so last in, first out for a stack, the operation used is the inverse of that. So instead of less than, it's greater than or equal, because you're going to be 100 is greater than or equal to I in this case. And that's just, I don't know, it's an oddity that you may or may not trip up on. And then the internal loop looks just the same, right? It's going to load 2, which is j, push the 100, going to compare, and then it does the jumps. And this is how the loops are exited. So if I is greater than 100, it jumps to L2, which is further down, which is outside the loop. This is, in this case, it'll jump to L5, which is here. And see, there's a frame chop again, whatever. This is where it increments I to the next thing in the loop, and then there's the goto, which Java doesn't have goto. And it goes back to L1, which is just up here at the beginning of the loop. And that's the basic form of the loop. It's rather simplistic, rather basic, but it's a classic, and it works, right? So what was it, Java 4, Java 5, I forget, introduced the for each loop, which introduced a certain amount of magic. It's largely syntactic sugar, but here's what the compiler does for you in order to give you this simplistic source form. So it's going to A-load 1, which is the first. In this case, I passed a parameter because I wanted the method body to be smaller without all the declarations of stuff inside the bytecode. In this case, it's going to load the argument that we send in, and we're going to call invoke interface, which is how you invoke a method against an interface, because there's an extra lookup. So I was talking to Brian yesterday and wanted to make the distinction between like what the static stuff, the source does for you, and what the compiler does dynamically. And this is one of those cases. So the invocation is statically bound to in this case, the iterator on method on the class list. So it's statically bound at compile time. This is what it's going to look for. At runtime, it's going to look what the actual type is on this reference, and it's going to find that method list there's a table that it looks up for making method calls. So that's how it resolves at runtime what body of code it's actually going to run, even though it's been told to run the code on list. That's invoke interface. But anyways, in the for each loop, you see we get a free iterator call, and it stores it in A2. Now, the interesting thing that I noticed about this one is if you come to the local variable table, there is no 2 in the local variable table. It's an unnamed variable. It's unavailable for reference inside your source code. There's no way to get at this iterator in the source code, which makes sense in a way. If you've ever tried to get that at the iterator, it's literally not available. You have to explicitly call it if you want it, and that's how that works. Anyhow, so we're going to load 2, which is the unnamed variable, the iterator we just got. We're going to invoke has next. If it has next, it's going to jump to L2. And that's the end of it. So if has next returns false, this returns true and it jumps, because it's the inverse, I guess. And then it's going to load invoke interface to call next to get the first item off the list. And this is where the cast happens, because the bytecode doesn't really know about generics. You can see that it stores some information about it, but in terms of like resolution, it doesn't record enough data. This is the erasure that you've heard so much about over the years. But this is how it makes sure that the item in the list is actually a string. If this check cast fails, you get the big stack trace and your program dies. And then it stores it in variable 3, which will be s. Down here, you'll see variable 3 is s. And then it does the body of the loop. In this case, it calls system.println. And that's a for loop. That's the for each loop. The if block, again, will look a whole lot like the loop. It just there isn't the looping bit, but you still it'll load it. It'll do the comparison, the greater than, and if that fails, it'll jump past it down to L1, which is the end of the thing, and return. So I know I'm blazing through some of this, in part because it gets a little bit repetitive, in part because there's like more interesting things to go. If I'm going too fast, please holler. You'll have to yell because I literally cannot see you. But you'll see the bytecode is like not as exotic as you thought it might be for most of the stuff, which for me is a good thing. So the while loop actually looks a whole lot like the for loop in many ways. The setup is different because the way the syntax works, but it's the same. You can see it loads the variable. It does the comparison against whatever your terminal value is, and then if the comparison fails, it jumps to the end of it, and you're out. And then again, here's your method body we're getting the static field of system.out because it's a static field on the system class, and then we're invoking the virtual method because it's a print stream, which is an interface, and then it calls the print line. And then here's the go to L0. It's just an unconditional jump back to the beginning of the loop. Now you'll notice in this loop that I never actually increment x, so that's a bug, but I never planned to run this code, so I didn't want to muddy the waters with extra bytecodes. Now, what I really wanted to show you is the switch, because this is actually surprisingly interesting when you get down into the code. So this is what the classic switch looks like. So again, I didn't want the local variable declaration stuff, so we pass in an x. We're going to switch on x, and you get these three cases. The first 1, 2, and 3, we're going to print it. If it's 4, we're going to print it times 2. If it's 5, we're just going to print it again. And then there are these breaks, because the classic switch falls through on each case unless you put in a break, right? So then what you see here, it generates a jump table for this switch, and here are your cases. You see 1, 2, and 3 all map to L1, label 1. 4 maps to label 2, 5 maps to label 3, and we have this default of L4, which we'll see down the way. And then L1 is literally, print line. We load it, we invoke virtual, like we saw before. And then we do a go to L6, which is after the switch, because we want to skip the rest of it. That's where the break comes in, mostly. L2, same logic. We just we load it, then we load the 2 constant, so we can call imul, which is a multiple on an integer type, and then we print that as well. And then for the last one, we just print x again. So that's a switch. It's pretty straightforward. Here's the default. Here at the end, we throw an exception. Otherwise, the compiler gets a little twitchy. And then we're done. And then you see we have these local variables. We have this, blah, blah, blah. The arrow switch, it was a pretty big syntactical change as far as how we write source code goes, and it looks a little bit like that. I don't need as much space for the bytecode half of the screen, so maybe that'll be. So from the source perspective, it was a pretty big change, right? Super nice, much more concise, easier to write. If you look at the bytecode, it is literally the exact same bytecode. I won't go through all of it because there are more interesting things to go to. But if you take a look, it's all literally, it compiles down to the exact same things. So the compiler gives you these extra conveniences to remove some of the burden, but in the end, it generates the same bytecode, which I thought was a little surprising. I thought it'd be something a bit more exotic. But now switch expression gets slightly more interesting. Again, it's the same basic cases, although I'm returning a value now, so it's a little bit different. And I used different types because I wanted to see what the bytecode would look like. But you still have the same kind of jump table, the switch table. So in the first case, in 1, 2, and 3 at L1, we're going to push 42. We're going to invoke static to get the value of little internal housekeeping. And then it says go to L5. And if we scroll down to L5, what L5 does, is it says a store 2. And if you look at local variable 2, you can see it's result, which you see here, which is our local variable, and the inferred type is serializable because it's the only common supertype of the 3 types that I gave it, which was intentional. And you can see here that idea kindly says, oh, that's serializable. But each step will do that. It does it whatever its logic is, and then they all jump to L5. You see there's go to L5, go to L5. This is the default case where it throws the exception. There is no go to, a throw, returns out of the method, unrolls the stack, and your application crashes. But they all jump to L5, which stores it in that local variable as we've asked it to, and then in this case, we do nothing with it. But it adds that one extra step so that when you use the yield keyword, you can pop that version back out of that particular case and assign it to a local variable. So that's the switch expressions, which is fun. I don't know if you've ever used the switch expressions, but I don't often use switch because I'm old, but it does come in handy. What's really interesting, for those of us who were in early years of Java, there was a point in time when you could not do switches on strings. You could only do switches on integer values, basically, because it used it to build this jump table. And it was a moderately big deal whenever string switches showed up. But they cheated, and what it does is, you can see here there's all this, load this, store this, blah, blah, blah. Down here's where the magic happens, and it literally calls hash on your string, right? And what does hash return? A long. Long is an integral type, not an int, whatever. And then you're just back at your lookup switch table again, and then you have these hash values that it uses to jump around. And that was the compiler magic that got us string switches, because they cheated, but it's helpful. And then there's just a whole bunch of stuff. These are all the branches. So those are how the basic flow control stuff works. Now, to get more interesting, if we look at generics, generics are surprisingly boring, which is not what I expected to see. So if we have this class, generics, you can see we have an unbound type T, and what that looks like, we'll see it here in better. You get a couple of things that we haven't necessarily seen before. I think they were there, we just kind of ignored them because there was nothing to see. So there are 2 parts to whether it's a class declaration and also a method declaration, because you can have generic methods. There is the descriptor, which is like the standard, it's been around forever. The signature, as I understand it, was added to aid in generic resolution. So method dispatch is technically used on the descriptor. This is fixed, typeless. All your generic types are just objects. But the signature helps hold what extra generic information it can. So even though the JVM operates under typically type erasure, there's a little bit of type information that is stored that can be referenced in certain scenarios. But you can't overload like list string and list foo, because the descriptor would just say Java util list, and then you'd have 2 methods with the same descriptor, and that's an ambiguous resolution. And we've all seen that error before. I had it just last week because I forgot that I had 2 generic lists as parameters. But that's really all it stores in terms of generics information. You have this signature. It gets more interesting with the subclass. I don't think it has it in this. We'll take a look at that one. And in the subclass, you can see the signature again, except this time we have, when we are extending it, you can see here we extend, this is the signature for the generics class, but you see we have the T bound this time to the string. So instead of just the unbound T, which is essentially Java-lang object, now we have the string bound in the signature definition. And you can see it comes over here, and then there's that. So it stores that type in the signature, which helps in resolution down the line, so that if you were to implement a method, which I don't think we're doing on this one, if you had a method that took whatever the type T was in generics, it could bind that to whatever your type is that you bound on the subclasses. And that's essentially how the generics work at the broadest strokes. All All right, yeah, I don't want to get too in the deep weeds. Generics can get fun, but let's look at generic methods more specifically, because there's some interesting bits there. So, right-click. When you look at this, all right, so we implement the consumer interface, which is like a standard interface on the JDK, and it takes consumer string. I have this here just to kind of show you the thing at work, and then the implementation of it. And then this is, you guys have written like a generic method where the generic definition type is like on the method itself and not on the class type. So we're going to take a look at how both of those look. And then I don't want to do a whole lot because, again, there's other stuff to get to. You can see the signature consumer, it's bound to a string. And then here's the constructor. Nothing terribly special with that, even with the generics in the mix. But then when it generates the method here, you can see here's the accepts string, like we see in our source code here, right? So that's the function that we wrote. But where it gets interesting is this. You get another method also called, oh wait, it's down here because I have the other method, called accept. And you'll notice that this one takes a Java-lang object. But there's a few things that are interesting to note here. You see this synthetic bridge. These are two flags that the JVM uses to signify a few different things. If you see a synthetic method, those are there so that the JVM can bind to it at the bytecode level, but they are not visible at the source level. So I can never call accept and pass in object because object is not a string. But the JVM can bind to it and resolve to that method in various scenarios where perhaps the type resolution hasn't been quite refined yet. But what it does internally is it does a cast to a string to make sure that whatever parameter gets passed into it actually is a string. And if that check does not fail, it will call invoke virtual on the actual accept method that takes the string. So this is a bridge method that can take a potentially untyped value. If you get it out of another list or whatever and you don't know the type of it at runtime, it can resolve this method at runtime and then do the check for you that it's a string and then call the actual implementation method. And this method gets generated by the compiler. You never see it from source code, and it's impossible to call because of the synthetic flag. I have a project that tries to play with that synthetics tag, but it breaks in weird ways because, again, it gets odd. All right, what do we got? It's 1:40. We have like 10 minutes. Again, I tried to combine all of this so we can get to some interesting things, but there's so much to look at. I don't want to look at auto-boxing. There's interesting stuff there, but it's not that interesting. What I want to look at, I'm going to look at two things briefly. I'm going to look at nested classes, because there's some fun stuff there. But what I really want to look at is lambdas, because that's the weirdest stuff out of all of that I looked at. But in terms of nested classes, so here we have a top-level class. Now, there are two ways to do nested classes in Java. You can have an inner class and nested class, and I know I'm using the same term. A nested class is just a class scoped within another class, but it's static. And an inner class is scoped to a particular instance, right? And the difference between those two is that an inner class has an implicit reference to the enclosing instance. And this is where you get a lot of memory leaks if you instantiate an inner class and you return that back out, and it goes off and does its thing, and your top-level class, you're done with it, and you let it go. It can never get garbage collected because your nested class, your inner class that you just returned out of your method, still has a reference to it. So it will stick around as long as this inner instance hangs around. Something to be aware of if you weren't already. But in the early days of Java, the compiler would build these synthetic methods internally so that in an inner class, you can access the private members or the non-public members of the enclosing type, right? It's a syntactical thing. Not everyone is aware that that's possible, but it's doable. And the way that used to happen is the compiler would generate these synthetic methods internally that would then basically bounce a request into the actual instance to return that value because the visibility rules interfered. And that was fine. It worked, but it was inefficient in a number of ways. And within recent versions, they started introduce. Has anyone heard of the whole concept of nestmates, if you follow any of that? So what nestmates do is it tells the compiler these classes all know each other. If you're familiar with the friend modifier in C++, it's very similar. It basically says, let these types access each other's non-public stuff. And you can see those entries as nest members here. And then down here in these other class, you'll have a reference for a nest host, which would show the top level type. Okay? And then with that bookkeeping information in place, the JVM no longer has to worry about accessibility rules when these types try to interact with non-public members of each other. Makes it a little bit more efficient. Certainly shrinks the size of the bytecode. And that's just your standard class. Now, we're almost, that's not what I wanted. This is what I wanted. We have like 5 minutes left. So let's do, I have some examples for lambdas, which are interesting, records, pattern matching, and sealed classes. I want to show you lambdas because it's like exotic and weird and interesting, but something else might be more interesting. Would you rather see any of the others or lambdas? I'm happy to go either way. Which one? Lambdas, that's what I want to hear. Sealed classes turned out to be rather boring, honestly. It's a bunch of entries like nestmates, except for like allowed members or something like that. I was hoping for some like really weird, but anyways. But lambdas are the interesting thing, and there's a whole lot happening here. Now this is a dumb method. If you want to say that method is why did you write that? It's because I needed bytecode to look at. It doesn't really do anything useful. So what lambdas use is invoke dynamic to get at what you're doing. Now, normally what happens when you call a method, you see that invoke virtual, which binds it to a particular type, right? But with invoke dynamic, you don't always have a type. Certainly if you have, in fact, we can see the type here where we have the variable r, and it's just the lambda. There's no actual type. I give it a type runnable just for illustrative purposes, but you could do this. I think, is the language level? Oh yeah, cannot infer. But it's a lambda, and by giving it the runnable type, that's where you get like the single abstract method, the SAM thing that was a big discussion when this came out. This is how this gets resolved. But this is just, it's like a bare function technically without a type. So what invoke dynamic does is it basically defers that particular binding down the line, so it dynamically decides where to do it. And how that happens is already you can see there's an inner class method handles lookup, which we'll see. We'll ignore the body because the body, we've already seen what the body does. But this is the interesting bit. You see the invoke dynamic, there's the method, the run, the type is runnable because we've given it a specific type, and then there's this stuff. So you have the lambda metafactory call, so we're going to invoke that static method that takes in a whole bunch of stuff, and it returns a call site, which is another JDK type. And then there's a function that takes no arguments, returns void, and then this is the lambdas are implemented as anonymous inner classes, typically in the class file. And so when we come down to the bottom, we can see this function. It's synthetic. Again, we can't call it. But this is the body of, you can see here, our system out println hello. You can see system out println hello. This is a constant. And then invoke virtual. So what happens is when you compile this, there is, let me show you the Java P version. This is where the Java P version is actually more interesting because the ASM version kind of inlines things for you so that it's a little bit more readable. But it gets really lost in the weeds. So here's that invoke dynamic call. The ASM like blocks it all into like a code block that makes it sort of digestible. But this is just the bytecode after bytecode. There's the invoke dynamic call. with a new thread, blah, 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 yada, yada. And when you come down to the bottom, I don't want to scroll too fast, I'm going to lose it. You start seeing this, bootstrap methods. So these methods are run on Bootstrap, and they bind basically the Lambda to the call site so that when you invoke the Lambda, it can resolve it dynamically at runtime later. And so all of this happens, and if you look at one last thing, why I don't like worrying about the constant pool is there is a lot that goes back and forth. Okay, it's really small on my screen, but you can see just in this very simple code, the constant pool just got massively huge. There's a method type, there's method handles, there's method refs, name and types, and it uses all these things at runtime bouncing back and forth to resolve all of these things to make your Lambda invocable. But it's also why, if you've seen the effectively final thing, one of the last things that it does, if I do a second call where I print line X, one of the last things that it does before it calls that is it loads iLoad3. So it loads that variable on the stack and then calls the invoke dynamic bits, which captures that value inside this method's stack, essentially. So technically, I think the bytecode will allow you to mutate that value after the invoke dynamic call, but because the method body of that Lambda could be called anywhere on a different thread, whatever, it's almost always going to be a bug, because you might see different state inside the Lambda than you expected, or you might expect the two to not affect each other. Anyways, the safe way was to say you can't do that. And I think, okay, that's officially it. There's a bunch more. So let me leave you with a couple of resources. So the presentation, if you want to see this, what there is to see is on my GitHub. The JBang script is probably the most interesting thing that dumps the ASM if you want to use that. So this is the first time I've given this session, and so obviously there's like some rough edges and some pruning and tuning and whatever to do. So if you loved it and you want some feedback, like focus more on this or skip that because that was not as interesting as that, I'd love to have your feedback. If you hated the session, that's the link you can use. So anyhow, you can find me on Blue Sky or in GitHub if you have questions. I'm happy to answer if I can, or I can maybe point you in the right direction. But please do give feedback, because it helps me, and certainly it helps the conference make a better experience for all of you guys. So that's what I have. Do we have time for questions?
No, that's after.
Okay. Find me after if you have questions. Thank you.